Hello everyone, welcome to the session on fluid power systems. I am Satish H, Assistant Professor, Department of Mechanical Engineering, Maharaja Institute of Technology, Mysore. So this session, it is a continuation of this module 2. The topics which are covered are in continuation of the module number 2. So these are the topics which I am going to cover today. So in this session, so the pump selection factors is the first topic. Okay, so we know that in an hydraulic systems, okay, or the fluid power systems, we have various components are involved. Okay, so in order to do the specific application, so we have, for example, we have a pump which drives the fluid through the system, and then we have a control valves in order to control the pressure, and then flow rate as well as the direction of the fluid, that is respectively called as the flow control valves, direction control valves, okay, and pressure control valves. So and also we have an actuator where the fluid energy is converted into the mechanical energy where the actual work is done. Okay, so and then we have a piping systems in order to connect all these the components together, and then we have a like of course the tank in order to store the hydraulic fluid, and then we have other components like filters in order to remove the solid contaminants which are present in the hydraulic system. Okay, so here in the first topic, so we are going to discuss like a pump is called as a heart of the hydraulic system. So that is a very important component which drives the fluid through the system. Okay, so here, so how do you select the pump? Okay, so what are the different factors that comes into the picture, okay, that are very important to consider while designing a pump? Okay, so those are the factors we are going to discuss. And then what is the step-by-step procedure, or what is the sequence of operations or the parameters you have to consider while selecting the pump, that we are going to see under the heading the pump selection factors. Okay, so the next one is pump performance characteristics. Okay, so like how good the pump is. Okay, so what is the efficiency? Okay, what is the like amount of leakage? Okay, so are any mechanical losses will be there, that is understood with the help of the parameter which are called as a volumetric efficiency, mechanical efficiency, and like overall efficiency. Volumetric efficiency gives an idea about how much is the leakage that is occurring through the pump. Okay, if there is a more amount of leakage is happening, then the volumetric efficiency of this pump comes down. Okay, so similarly the mechanical efficiency is the power losses or the energy losses inside the pump other than the leakage. Okay, so what could be the other reasons are, so it could be because of the wear of the moving parts. Okay, so or like some of the other like bearings. Okay, we have bearings. Okay, there is a losses of energy in the bearings as well. So other than the leakage, if there are any losses, okay, that will categorize into the mechanical energy losses that we can find out, okay, using like a mechanical efficiency. Okay, and overall efficiency of the pump, okay, so is like what are the total losses that is incurring, okay, that is occurring inside the pump. Okay, so that might include the energy loss due to the leakages, both internal as well as external leakages, as well as because of the mechanical losses, that is like a loss in the bearings, as well as losses due to the moving parts. Okay, so that whole thing comes into the like a overall efficiency. Okay, so under these headings, that is pump performance characteristics, we are going to write an expression for volumetric efficiency, how to calculate the volumetric efficiency using the actual flow rate and then the theoretical flow rate. And then we have a expression for mechanical efficiency that is represented by nu m. So and as well as we are going to write the overall efficiency. Okay, that is nu naught. Okay, so after writing or understanding these all the three types of efficiencies or the performance characteristics of the pump, so we will take one of the numericals. Okay, based on these the expressions. Okay, so in order to if the data is given, okay, if they ask us to find out the overall efficiency or the mechanical efficiency, okay, so how to do that, those problems we will consider at the end of this session here. Okay, so that is the different topics that we are going to cover or see in this session. Okay, so to begin with, the first topic, that is the pump selection factors. Okay, so as I said before, the pump is the heart of the hydraulic system, so that plays a very important role. Okay, while selecting the pump, you should consider various parameters. Okay, so some of these parameters are, so the flow rate requirements. Okay, so what do you mean by the flow rate is, which is normally expressed in the units, okay, that is meter cube per second. Okay, so how much amount of fluid is coming out of the pump at the outlet of the pump. Okay, so that also one of the factor which you have to consider while you are selecting a pump for a particular application. So and then we have operating speed. Okay, so we know that this pump is driven by the prime mover. Okay, normally the prime mover that we use in an hydraulic systems or a fluid power systems is the motor, electric motor, the speed of this electric motor, so that is also very important. Also selection of the motor also very important in this case. Okay, so next we have a pressure ratings. Okay, so pressure rating, like how much pressures, okay, with which the fluid power system or the hydraulic system after designing everything, okay, it is operating, that is also very important. Okay, the pressure of the fluid is required. Okay, so we know that there is a resistance to the flow of fluid, because at the actuator we have the load we are applying, the fluid has to move against this resistance. Okay, so it has to take that load, okay, through some distance, for example. So that pressure decides, okay, so it is proportional to the amount of load that is the fluid power system is lifting. Okay, so our load that is coming on the fluid power systems. So and also we have the maintenance cost and then the noise. Okay, so of course for a good designer of an hydraulic system, we should look for that hydraulic system should have a less maintenance. Okay, and then overall cost of this the hydraulic system or the fluid power system should be less. Okay, so these are the some of the factors. And the noise, okay, which is also an important factor. So after since it involves various components, for example like a pumps and then actuators, and we have the valves, etc. So these are moving components. Okay, so when they are operating, okay, there is of course the noise will be the one of the factors. So we are basically relatively quieter the hydraulic system or the fluid power systems. Okay, we are indent to the design. Okay, so these are the some of the important factors so we have to look for. Okay, so and then as the heading says, okay, pump selection factors. So there are a sequence of operations or the sequence of like a parameters we have to consider while selecting a pump. Okay, so it has to go in a step-by-step procedure. Okay, so like it has to one important parameter you have to select, and then from that you have to derive all the important parameters from that one. Okay, so it is a sequence of operations or the step-by-step procedure that we have to follow while selecting a pump. Okay, so let us see what are those step-by-step procedures or the sequence of operations one by one. So first one is the actuator selection. Okay, so actuator is where the work is done, okay, in an hydraulic system. So at the actuator, basically the fluid energy or the pressure energy or the hydraulic energy is converted into the mechanical energy. Okay, so for example the lifting of a weight at the actuator end. Okay, so that is taking place at the actuator. Okay, so and then here you have to, actuators is also called as hydraulic cylinders. Okay, because it is kind of a piston and cylinder assembly, or they are called as a hydraulic motors. Okay, so this selection of an actuator, it depends upon the loads which are coming onto the hydraulic system. Okay, so how much load that is a hydraulic system has to lift, or how much work it has to do at the output. Okay, that depends upon the type of the actuator. Okay, so you are selecting there. Okay, so that is the first and foremost step you have to do while selecting a pump. Okay, so and then the second one is determine the flow rate requirements. Okay, so determining the flow rate requirements. Okay, flow rate, as I said, it is amount of fluid that is at the outlet of the pump. Okay, that is normally measured in terms of the meter cube per seconds. Okay, so this is the second step. Okay, so we have to determine the flow rate requirements. Okay, so this involves the calculation of the flow rates. Okay, so that is is normally in meter cube per seconds. Okay. So and then the third important factor is system pressure selection. Okay. So where the system pressure is another important parameter. Okay. So why? Because it decides, okay, the size of the actuator, okay, as well, because the resistance against the flow of the fluid inside the hydraulic system, because the resistance to the fluid inside the hydraulic system is developed because of the what are the different types of the loads which are coming on the hydraulic system. Okay. So our working pressure, okay, or the pressure of the hydraulic system or the hydraulic fluid is should be in a such a way that it has to overcome that resistance which is coming because of the like a loads which are coming onto the hydraulic system or a fluid power system. Also it has to like overcome the pressure that is coming, okay, because of the flow of the fluid inside the pipelines. Okay. So considering that factors, the third important parameter is that is the selection of hydraulic pressure, or the system pressure selection is very important. Okay. Next is determine the pump speed and then select the prime mover. Okay. So the pump speed, okay, as we know, this pump is driven by the prime mover, normally the electric motor. That prime mover is running at certain speed, okay, which is driving the like a pump. Okay. So while selecting this speed, okay, you are also in turn selecting this the prime mover as well. Okay. So the speed is normally it is a revolutions per minute, RPM, it is measured in. Okay. So that we have to select. Okay. So along with the speed, okay, along with this flow rate calculations, okay, so we can decide the volumetric displacement of the pump. Okay. So along with the speed as well as along with this the flow rate requirements, okay, you can decide the volumetric, okay, volumetric displacement of the pump. Okay. So that means how much volume of a fluid is going out of the pump per revolution. Okay. So this in turn decides the size of the pump, okay, because volumetric displacement is directly proportional to the size of the pump. Okay. So that is the next factor what we have to consider here. Okay. So after this the point number 5 are the step, okay, or the sequence of operation. Number 5th is select the pump based on the application. Okay. So we know that, okay, in the previous classes you might have studied the classification of the pump. Okay. So in the first like a session of this second module, so we have like a classifications like positive displacement as well as non-positive displacement pumps. Okay. So positive displacement pumps, again they are classified as the rotary pumps and the reciprocating pumps. Okay. So under the rotary pumps we have studied, okay, or understood the working and construction, okay, or construction and working of like a gear pumps, okay, vane pumps, and then the piston pumps. Okay. So and then we have also understood what you mean by the variable displacement and fixed displacement pumps as well. Okay. So under the gear pumps we have studied different kinds. Okay. For example, we have an external gear pump, okay, internal gear pump, lobe pump, okay, so etc. Similarly in a vane pump also we have a different types of pumps we have studied. Okay. Among this broader classification, it doesn't mean that, okay, like a one pump like is suitable for all the applications. Okay. So based on the application, okay, of this hydraulic system or the fluid power system, you have to select the pump, okay, type of pump which you are going to use for that particular hydraulic system for a particular applications. Okay. So that is a next step. Okay. Next is select the reservoir and associated plumbing, including the piping, valving, okay, and filters and strainers and accumulators. Okay. So once you select this like a type of the pump, okay, so we have already decided the actuator, also we have decided the like a pump as well as a prime mover. Okay. So once you have all this data, you can, based on that, you can select the tank, okay, or the reservoir, so where the hydraulic oil is stored. Okay. So and then we can select the like a piping systems. Okay. So we also discussed in the previous sessions, okay, what are the different types of pipings we can have. Okay. For example, steel pipes or steel tubings or flexible hoses. Okay. So we can select like which type of the pipings you are going to use for the hydraulic system. And then the valving, okay, valving. So valves are the control devices, okay, they control the pressure as well as they control the flow, direction of the flow of the fluid inside the hydraulic systems, and then they also control the flow rate, how much amount of fluid should flow through the valve, okay. So that is controlled by the valves, okay. So after selecting this the piping systems as well as the reservoir, you have to go for this selection of this, okay, the pipings, and then valvings, okay, valves, okay, different types of valves. And then filters and strainers, okay, we have also discussed about what are different types of filters, how do you classify the filters, and also where do you place the filters, okay, depending upon that classification we have studied. The filters are nothing but filters and strainers, they remove the any solid contaminants, okay, so which are present in the oil, okay. So before they are harming or they are having an effect on other components of a hydraulic system. For example, it could be a pump or the valves or the actuators, okay. So that we will discuss, that we have to select what type of the filters you are using, what type of the strainers we are using, okay, in the next step. And then the accumulators, okay, so these are the various components, okay, in the like step 6, okay, you are going to select. And then the next one is 7th one, consider factors such as noise levels, horsepower loss, need for heat exchangers, and then pump wear and scheduled maintenance, okay. So after having decided on the various components of the hydraulic systems, okay, there are other parameters also, what is the noise levels, is there too high, okay, or too low, okay, so or it is optimum, okay, that way you have to decide, okay, what is kind of noises that is occurring in the hydraulic systems, okay. And then heat exchangers, okay. So heat exchangers is when the fluid is operating under the pressure, okay. So it will undergo like a temperatures, increase in the temperatures as well, okay. So in order to remove this the heat, okay, or the temperature from this heat from this hydraulic fluid time to time, okay, like within the reservoir or providing an external devices like a fan, okay, so or a radiators, okay, so you can remove that, okay, so that we can decide here. So need for heat exchanger, does really our hydraulic system needs a heat exchangers, that you have to decide, okay, as an hydraulic fluid power system design engineer, okay. So and then schedule maintenance and pump wear, okay, so how much is the pump wear over the operation of this pump, and then the schedule maintenance, okay. So when the fluid power system or the hydraulic system that you are designing, okay, it has to be maintained, okay, so time to time that schedule has to be decided, okay. So these are the various vector. And then the last one, number 8th one, is the calculate the overall cost of the system, okay. This is a very important even though it is a last operation in the sequence of operations, but it is a very important thing. So we are looking at a efficient hydraulic system which is also cost effective. That means it should perform the desired operations, okay, so efficiently without any losses, and it should have a lesser cost, okay. So thus cost is very important parameter, okay, so while designing an hydraulic system, okay. This is, we calculate the overall cost of the system, okay. This is about all the 8 steps or sequence of operations, so that are involved while in the pump selection factors, okay. So the first one is if I repeat, that is actuator selection, and second one is determining the flow rate requirements, third one is determine the pump speed and select the prime mover, okay. Speed and prime mover are interrelated, okay. So and then select the pump based on the application, okay. So there are various types of pumps available, you have to select them which is suitable for that particular application, and select the reservoir and associated plumbing, okay, including piping, valving, filters and strainers, okay. These are the other components other than like a pump, and then selecting an actuator, okay. And then these are the various other components of an hydraulic systems that you have to select, and then consider the factors such as other outside factors like noise levels, okay. So and then is there a pump wear, what is the maintenance of this hydraulic system, those things you have to consider. And last one, which is very important, so you should have a very cost effective, that means hydraulic system should cost less, okay. So these are the various sequence of operations, okay, so you have to consider while selecting a hydraulic system. So after understanding the pump selection factors, so we will discuss about the pump performance. Okay, so under which we have a volumetric efficiency that is represented as nu V. Okay, so what is the significance of volumetric efficiency is, okay, here you can understand, okay, how this pump, okay, or the power loss inside the pump due to the leakages that is happening inside the pump. Okay, so as we know that, okay, so there is a leakage of hydraulic fluid, okay, inside like a internal leakage as well as external leakage. Okay, in the case of the pumps, we have a rotating parts, okay, which are inside the casing. Okay, in order to accommodate for the rotation, we have to provide the clearances. Okay, so through those clearances, okay, there is a certain amount of leakage, that is internal leakage is happening. Okay, so because of that, okay, you can't get a 100% efficient pump. Okay, so there will be always a losses, okay, due to the leakages that are involved. Okay, so that volumetric efficiency captures, okay, so the energy loss inside the pump, okay, due to the leakages. Okay, so the volumetric efficiency that is represented by nu V. Okay, so it is defined as it is a ratio of, okay, actual flow rate, okay, so produced by the pump. It is a ratio of actual flow rate produced by the pump, okay, that is in the numerator, to the theoretical flow rate that pump should produce. Okay, so this is divided by theoretical flow rate pump should produce. So it is a basically ratio of the flow rates. In the numerator, we have an actual flow rate that is produced by the pump. Okay, so in the denominator also we have a flow rate that is theoretical flow rate, okay, pump should produce. Okay, so in terms of notations, if you write, okay, the actual flow rate is represented as Q suffix T, and then a theoretical flow rate is represented as QA or Q suffix A. Okay, so if you write that nu V is equal to, okay, actual flow rate, okay, that is produced by the pump is QA time, okay, divided by, so in the denominator we have a theoretical flow rate that is QT. Okay, so basically the volumetric efficiency is the ratio of actual flow rate to the theoretical flow rate. Okay, so if you take this different types of the pumps, okay, we know that we have a gear pumps, vane pumps and piston pumps. Okay, so normally we will see what is going to be the volumetric efficiency of these pumps. Okay, so the first one is, okay, so that is volumetric efficiency of the gear pump. Okay, for the gear pump, volumetric efficiency of the gear pump, it will in the range of 80% to the 90%. Okay, 80 to 90%. And then we have the vane pumps. Okay, they have the little bit higher volumetric efficiency, that is nu V is equal to, so vane pump, okay, little bit higher efficiency than the gear pumps. They have something like 82 to, okay, 92% of volumetric efficiency. So and then we have the piston pumps. They have the highest, okay, compared to these two. Okay, so that is, so new volume for piston pumps. Okay, so this is equal to 90% to 98%. Okay, so this is about the volumetric efficiency. What you have to remember is volumetric efficiency is the basically ratio of the flow rate. In the numerator, it is the actual flow rate. In the denominator, theoretical flow rate. Okay, it is the ratio of actual flow rate produced by the pump to the theoretical flow rate pump should produce. Okay, so this is nu V is equal to, in terms of notation we can write it as QA divided by of QT. So we have written the volumetric efficiencies for some like the different types of pumps, that is nu V for the gear pump is 80% to the 90%, and nu V for the vane pump is about 82 to 92%, and nu V for the piston pump is 90 to 98%. Okay. So the next parameter that we want to define is the mechanical efficiency. So that is mechanical efficiency, that is represented by nu suffix m, nu m. So the mechanical efficiency is basically the energy losses inside the pump other than leakages. Okay, so what are the other factors, okay, that leads to energy losses inside the pump are, okay, we know that there are moving parts inside the pump. Okay, so due to that moving parts, okay, there are energy losses due to the wear of the moving components. Okay, so those are the some of the reasons, okay, which leads to the mechanical efficiency. Okay, so also mechanical efficiency is from the turbulence of the fluid, okay, which is inside the fluid. Okay, so that is also leads to the mechanical efficiency. Okay, so are the energy losses, okay, that will accommodate into the mechanical efficiency. Okay, so the mechanical efficiency normally is in between 90% to the 95%, 90 to 95%. Okay, how do you define this mechanical efficiency? Okay, the mechanical efficiency, that is nu m. Okay, so it is a ratio of, okay, so pump output power, assuming no leakage, okay, to in the denominator actual power delivered to the pump. Okay, so actual power delivered to the pump. Okay, it is a ratio of pump output power assuming no leakage to the actual power delivered to the pump. Okay, that is written as nu m is equal to, that is P times Qt, that is theoretical flow rate, divided by TA into N. Okay, let us look at what are these different parameters which are involved in this formula. So the P is, that is pump discharge pressure. P is pump discharge pressure, that is normally given in terms of pascals, that is a unit for a pump discharge pressure. And then we have Qt, that is theoretical flow rate, okay, that is given in terms of meter cubes per second. Okay, that is P is pump discharge pressure, units are pascals, and Qt is theoretical flow rate, that is meter cube per seconds. And then we have TA, that is actual torque, TA is actual torque delivered to pump, okay. So the torque is normally represented in terms of, the units are Newton meters. Okay, so that is Newton meter. And then we know that capital N is pump speed, okay. So the pump speed, the units are RPM, that is revolutions per a minute. Okay, so this is RPM, that is revolutions per minute. Okay, so this is how you have to write an expression for mechanical efficiency. Okay, nu m is the ratio of pump output power assuming no leakage to actual power delivered to the pump. It is written as P into Qt divided by TA into N, where P is the pump discharge pressure in pascals, and then Qt is the theoretical flow rate, that is in meter cube per seconds, and TA is the actual torque delivered to the pump, that is in Newton meters, and then N is the pump speed, that is given in terms of the RPM. So there is one more way in which we can find out this mechanical efficiency. So that is given by, so that is nu m is equal to theoretical torque required to operate the pump, okay, that is in numerator, divided by actual torque delivered to the pump, okay. So that is the ratio of the torques. Actually in the numerator we have a theoretical torque, and in the denominator we have an actual torque, okay. So by using these notations we can write it as nu m is equal to T divided by TA, okay, where T suffix T is the theoretical torque and then TA is the actual torque, okay. So here the theoretical torque, okay, so TT can be given as Vd into P divided by 2 pi, where Vd is a volumetric displacement, okay, that is normally expressed in meter cube per revolutions, and then the P is the pressure, that is in pascals, okay, divided by 2 pi, and then actual torque is given by W divided by N, okay. So if we have this N, that is the speed of this pump in radians per second, okay, now to convert that, okay, so you have to multiply that with the 2 pi by 60, okay. So this radians per second is converted into the revolutions per minute, okay, by multiplying that with the 2 pi by 60, okay. So these are the two methods in which we can calculate the mechanical efficiency, okay. The last the efficiency or the performance characteristics is like overall efficiency, okay. So what does this overall efficiency represent is, okay, total amount of losses that is incurring or occurring inside the pump, okay. That could be because of the internal leakages, external leakages, okay, as well as due to the like a wear of moving components, etc., okay. That both includes the volumetric efficiency as well as the mechanical efficiency, okay. So that overall efficiency, which is normally represented as nu naught, okay, nu naught is given by actual power delivered by the pump, okay, divided by actual power delivered to the pump, that is output by input, okay. So that is actual power delivered by the pump to the actual power delivered to the pump, okay. So this is a multiplication of, okay, the volumetric efficiency and then the mechanical efficiency, okay. So that means to say nu naught is equal to nu V multiplied by nu M, okay. So that can also be written, okay, in other ways as P times QA divided by TA into N, okay. What do you mean by P is, it is the pressure which is expressed in pascals, and then QA is Q means the flow rate, okay, meter cube per second are the units for that, and then A represents the actual flow rate, okay, that is QA is the actual flow rate divided by TA, okay. So T represents the torque, okay, that is in Newton meters, TA represents the actual torque, okay, so that is in Newton meters. The pump speed is given by, so N, capital letter N, that is in terms of the RPM, that is revolutions per minute, okay. So this is, so now let us discuss the problems or the numericals which are based on this performance characteristics of the pumps, okay. So the problem, the first problem is like this: a pump has a displacement volume of 100 centimeters cube. It delivers a 0.0015 meter cube per second, so at 1000 RPM and 70 bars. If the prime mover input torque is 120 Newton meter, then what is the overall efficiency of the pump, okay. So and then next is, what is the theoretical torque required for the pump, okay. So this is a problem. So let us collect the given data, okay. So what are the given data in the problem is, so the first one is a pump has a displacement volume of 100 centimeter cube, okay. So what is the displacement volume is represented as Vd, so that is Vd is equal to 100 centimeter cube. So we keep everything in terms of the meters, okay. So that is why we convert this into the meters, that is 100 into 0.01, okay, whole cube. This is in meter cube, okay. So this is 1 centimeter is equal to 10 to the power of minus 2 meters, okay. So that is why 100 into 0.01 whole cube into meter cube, okay. So if I simplify this, you will get it as 0.0001, okay. So meter cube per second, I am sorry, meter cube per revolution, So that is the units for volumetric displacement. Okay, so Vd is given in centimeter cube. We converted that into the meter cube, and then the units for this is meter cube per revolution. Okay, so what else is given? If it delivers 0.0015, okay, so that is at 1000 rpm. Okay, the speed is given and also the actual flow rate is given. Okay, so that is QA is equal to, okay, so the pump it delivers 0.0015. Okay, so that is the units for this flow rate is, that is meter cube per second. Okay, so and then the pump speed is given, that is N, the capital N is equal to, I will write it here only. So capital N is equal to 1000 rpm. And then the pressure is also given, that is equal to the 70 bars. Okay, so since we are keeping everything in the meters, okay, we have to convert that into the newtons as well as meters. Okay, so that is P is equal to 70 bar. So this is equal to 70 into 10 to the power of 5 newtons per meter square. Okay, so this is the pressure it has been given. Okay, so and then if the prime mover input torque, okay, is 120 Newton meter. Okay, so what is asked us to find out is a theoretical torque they are asked us to find out, and then actual torque is given. Okay, so that is TA is equal to, okay, actual torque is how much? 120 Newton meter. So torque is, the units for the torque is newtons meters. Okay, so what is they ask us to find out is what is the overall efficiency of the pump. Okay, so that is represented by nu naught is equal to question mark, that is ask us to find out, and then what is the theoretical torque required to operate the pump. Okay, so that is T is equal to question mark. These are the two unknowns we have to find out. Okay, so first thing is we need to find out the overall efficiency. For finding out the overall efficiency, we need, okay, the two other efficiencies, that is volumetric efficiency and then the mechanical efficiency. Okay, so in order to find out the volumetric efficiency, we have the formula. Okay, so that is nu V is equal to actual flow rate divided by the theoretical flow rate. Okay, so volumetric efficiency is equal to actual flow rate divided by the theoretical flow rate. Okay, if you look at the data here, the actual flow rate is given, so that is equal to 0.0015, but the theoretical flow rate we have to find out. Okay, so what is theoretical flow rate? Okay, so QT is equal to, so that is given by Vd into N. Okay, that means volumetric displacement times the speed of the pump will give you this the theoretical flow rate. Okay, so what is Vd? That is volumetric displacement. If we come back to the data, the Vd is given, that is 100 centimeter cube. We have converted that into the meter cube per revolution, that is 0.0001 meter cube per revolution. Okay, so I am going to substitute this, so 0.001. Okay, so that is in terms of meter cube per revolution. I am going to write the units for the understanding purpose there only. Okay, so and then which is multiplied by, so N, what is N? The speed of the pump. Okay, what is given? The speed of the pump is given as, okay, 1000 rpm. So we have to substitute that into the, in terms of RPS, that is revolutions per second. Okay, so in order to convert this revolutions per minute into the revolutions per second, what you need to do is you have to divide that 1000 divided by the 60. Okay, so I am going to write, this is 1000 divided by 60. I am going to write the units as well here. Okay, so this is RPS. Okay, that is revolutions per second. Okay, so now if you multiply this, okay, so you get the theoretical flow rate as 0.00167. Okay, so that is in terms of meter cube per second. Okay, so that is the units for, okay, the theoretical flow rate. So this is the first unknown we have to find out. So from this, okay, if you look at this formula, in order to find out the volumetric efficiency, we have to substitute for QA and QT. What is QA? Actual flow rate. It is given in the problem, that is 0.0015 meter cube per second. We have found out this QT, that is theoretical flow rate, that is 0.00167. Okay, so we will do this. Okay, so that is volumetric efficiency is equal to, I will write it again, QA divided by QT. So QA is equal to, so what, how much? 0.0015, 0.0015, okay, divided by what is value of QT, that is 0.00167, okay. If you simplify this, okay, so you will get this, the volumetric like efficiency as, okay, 0.898, okay. So if you write it in terms of the percentage, you will get it as 89.8%, okay. So this is the volumetric efficiency, okay. So in order to find out the overall efficiency, we know that overall efficiency is the multiplication of the volumetric efficiency and then the mechanical efficiency, okay. So we have found out the mechanical volumetric efficiency. Next what you have to do is you have to find out the mechanical efficiency, which is given by, okay, P times QT divided by, so TA into N, okay. So here the terms are, so P is the pressure, okay, so in newtons per meter square. So whereas for us they are given it in terms of the bars, we have converted already into the newtons per meter square. If you multiply that with 10 to the power of 5, you will get it in terms of the newtons per meter square, okay. So after this, what else is given? So QT, okay, we know that is 0.00167 that we have calculated from this year, okay. So and then TA, that is actual torque is given, that is 120 Newton meter, and then the speed N, okay. So you have to note down here that, okay, you have to be careful while substituting for the N, that is the speed of the pump, you have to substitute that in terms of the radians per second, okay. So you have to multiply this with 2 pi by 60, okay, then you will get it in terms of a radians per second, okay. So let us substitute these values. So what is pressure? Pressure is, okay, so 70 bars, okay, that is 70 into 10 to the power of 5, 70 into 10 to the power of 5. I will write the units here for simplification, that is in newtons per meter square, and then what we have is QT, that is a theoretical flow rate, okay. From the previous calculation, we have calculated the theoretical flow rate as 0.00167. What are its units? Meters cube per second. Okay, so numerator is done, that is P into QT. P is the pressure, 70 into 10 to the power of 5, and then QT is the theoretical flow rate, that is 0.00167 meter cube per second. What is in the denominator is, okay, actual torque, okay. Actual torque is given in the problem, that is 120 Newton meters, okay. So this I am going to substitute. So this is 120, so that is in Newton meter. So which is multiplied by N, as I said before. So you have to substitute the N, that is speed of the pump, in radians per second, okay. What you have to do is, whatever the RPM is given, 1000, that you have to multiply by 2 pi by 60, okay. So this will be, so 1000 multiplied by 2 pi by 60. So you will get this mechanical efficiency as, okay, so 0.930. If you write it in terms of the percentage, you will get it as 93.0, okay, percent. So this is a mechanical efficiency of the pump, given pump, okay. So we have this volumetric efficiency and the mechanical efficiency. So we know that the overall efficiency is a multiplication of these two, that is mechanical and then the volumetric efficiency. Let us do that. So new volumetric is equal to new overall, okay, is equal to volumetric efficiency, that is nu V, multiplied by mechanical efficiency, that is nu M. So what is the volumetric efficiency of the pump? This is 0.898, okay. So we have to take this 0.898, so which is multiplied by, so what is the mechanical efficiency of the pump, which is equal to 0.930, okay. So this is equal to 0.930, okay. So if you simplify this, you will get this overall efficiency as, okay, 0.835. If you write it in terms of this percentage, you will get, you can write it as 83.5%. So this is equal to 83.5%, okay. So after this is the solution for the first question, that is what is the overall efficiency of the pump, okay. So this is answer for that. So that is 83.5% is the overall efficiency of the pump, okay. So the next question is, what is the theoretical torque required to the pump, to drive the pump, okay. So that is, okay, so I will write this as sub question B, okay. So we know that, so new mechanical, that is mechanical efficiency can also be written as, okay, so that is theoretical torque divided by the actual torque, okay, that is T divided by TA, okay. So what is given to us, okay, they have given this actual torque here, that is 120 Newton meter. We know the mechanical efficiency, that is 0.935. So by simplifying this, we will get this a theoretical torque required to drive the pump, okay. So this implies, so theoretical torque is equal to multiplying that mechanical efficiency, that is nu m, which is multiplied by, so actual torque, okay, that is TA, okay. So what is mechanical efficiency here? 0.93, okay, which is multiplied by actual torque, okay, that is given in the problem, that is 120 Newton meter, okay. I am going to substitute that value. So this is equal to 120. So after simplifying this one, okay, you will get this theoretical torque, okay. So that is T suffix T, okay, as 112 or 112 Newton meter, okay. So this is the answer for the sub question B, okay. So and then this is the answer for sub question A, that is overall efficiency of the pump as well as theoretical torque of the pump, okay. That is how you have to solve the problems which are based on the pumps.